Like any other class that you take during your studies, you may have this question, why am I taking this class? This is a class that will allow you to design really big realistic chips. We've had students going out of this class going into right into the teams that doing the biggest, most sophisticated hardware that goes inside the modern computing systems. Here is a picture that I've borrowed from Professor Varna, who's the other instructor who's teaching this course. And he is part of the Qualcomm design team, and this is something, the latest Snapdragon mobile processor that they've all designed end-to-end using the system Verilog. As you see here, this is a processor with multiple higher block modules. It's not feasible for really a one human or even set of human to manually design such a sophisticated system and have this billions of transistors lay out to do this highly complex chips. This course or the system Verilog learning this language will allow you to make a scalable design using tools that you will learn in this class, but based on the basics of the basic logic design course that you've hopefully taken as a prerequisite to this course. You could express design with code instead of expressing it with like layout or schematic that you may have learned in your prior digital design course, or maybe even like the Carnot maps that allowed you to make circuits with 4 or 5 variables at most. You don't see the complexity of the hardware, and then the nice thing is we don't do things manually like you've probably designed circuits with Carnot maps and try to optimize those boxes for 4 or 5 variables at most. Now we have this great tools at our dispense. These tools have been developed for more than 50 years in industry. These are automated tools that actually synthesize, which means that they take the description that you write in form of a code and they generate hardware for you. And not only they generate it, they also optimize it for you. Most of the modern circuits, system on chips, and the IPs that go inside hardware are designed using the system Verilog language. The nice thing is system Verilog can be used for making both custom chip, which is also dubbed as application-specific integrated circuit or ASIC, and FPGA. And most of the electrical computer engineering jobs are for system Verilog or Verilog chip-based design. It is not just that we are learning this to design some chips that are left over, but or connected to a bunch of computer at someone's home, but it actually, the FPGAs or programmable hardware has scaled so much. Now we have the FPGAs on most of the cloud platform. For example, the Microsoft Catapult project from the Azure team has deployed the FPGAs as a separate plane of computation that is added to its CPUs with routers. And all of the IPs that went into designing this cloud system are designed using Verilog and system Verilog. Not just that, if you want to use the capabilities or speeding up your designs using this custom programmable hardware, you need to know system Verilog or Verilog to remotely log in and use this cloud. FPGA cloud are also, and this is an example of the project Brainwave when they used the programmable FPGAs to make the some of the computing units for their machine learning systems on the cloud. This is another design from Microsoft Project Brainwave that was presented a couple of years ago. This is not just limited to Microsoft. Also, Amazon and many other cloud providers are migrating into having FPGAs integrated within their cloud and using Verilog system. Verilog would enable you to design for that custom cloud system. For the next set, we will be talking about the career paths in VLSI design and how you could use the knowledge in this class to get real jobs.